Hello, my name is Marisa Cantarino, and I'll talk about part of my PhD thesis together with my advisor, Regis Varão. In hyperbolic dynamics, we are interested in the behavior of maps in which the tangent bundle splits in two different directions, one with expansion and another with contraction. If these rates of contraction and expansion are uniform, we say that the map is Anosov. The classical example is this linear Toral automorphism given by this matrix. It has integer entries, so it induces a map on the torus, and since its determinant is 1, it has an inverse in the torus, so it's invertible map on the torus. It has an eigenvalue with norm greater than 1 and another with norm lesser than 1. So we have this direction V1 with expansion and another direction V2 with contraction. When we apply it to this little square that represents the one-dimensional torus, and each copy of this square in the plane is the same torus, we have this quadrilateral here that has area 1, because the determinant is 1. Then we can put together the pieces again here to form a square, because this is invertible. This is the classical case. But the non-invertible case is a bit different. So here we have an example. It's a linear Toral endomorphism, because since the determinant of this matrix is 3, it's not invertible in the torus. Then again, we have a direction with expansion, V1, and a direction with contraction, V2. And when we take this little square here and apply this map, we have another quadrilateral, but with area 3. Then each one of these points are the same point in the torus, but here in the plane, each one of them has a different preimage that gives a different preimage on the torus. These 3 points are different in the torus. So this is a covering map with degree 3, and each point has 3 preimages. Since the unstable directions may depend on the path of a point, a given point may have more than one unstable direction. This is the main difference between the invertible and non-invertible case. This can obstruct the conjugacy. So, in general, Anosov endomorphisms are not structurally stable, because conjugacies should preserve unstable directions. And we may have nearby maps, one of them with a number of unstable directions for a point, and another with another number of unstable directions for a corresponding point, and this obstructs conjugacy. But in the universal cover level, we have a conjugacy H, this big H here, and in general, it does not project on the torus. This conjugacy between F and its linearization. And we have it does descend to the torus only in the case in which each point has only one unstable direction, and we say that the map is special. Well, to give our rigidity results, I need to state this property about the regularity of the foliations. UBD stands for uniform bounded density, and it's a kind of absolute continuity, because this conditional measure is equivalent to the Lebesgue measure on the leaf. But not only they are equivalent, we have this uniform bounds here. This is a high regularity condition on the leaves. So our results are the following. If the stable and unstable foliations have this regularity condition, this UBD property, then the Lyapunov exponents of F and A are the same. In particular, the Lyapunov exponents of F are constant. Another result is a slight generalization of a result by Fernando Messena, in which we have the following. If F and G are CK Anosov endomorphisms, and they are conjugated by a map homotopic to identity. If the corresponding periodic points of F and G have the same Lyapunov exponents, then this conjugacy is as regular as the maps. And if they are same-finity, this conjugacy is same-finity. Joining these two results, we have this characterization of a smooth conjugacy, provided that there is a conjugacy. That's why we ask F to be special. Then there is a conjugacy with its linearization, and this UBD property in both the stable and unstable foliations is equivalent to this conjugacy being sem infinity. Thank you.